Really is an invited talk. Sorry about that, Richard. But at least you got a chance to do the joke. York is from Princeton University. He's a colleague from the Pear Lab and a physicist with wide-ranging interests. And I am looking forward to seeing what he has to say about advanced propulsion and conservation laws. York.
Okay, well, let me begin by talking about what this talk is not. I'm not going to be discussing warp drives or any other technique for moving faster than light. When I use space propulsion in the title, I simply mean taking an object, preferably a spacecraft, and getting it to move through the three-dimensional space that we're all familiar with at speeds slower than light. So, as an outline, there are a number of systems that we know for space propulsion that are in use, and I describe them as having failings because generally they do less than we'd like. I'm going to discuss why some of these failings seem to be mandated by physical law, some theoretical alternatives that may allow better propulsion systems to exist. I'm going to review some specific proposals for such systems, but I ask the audience to remember that all of these specific proposals are speculative. So let's start with the basic rocket. You move something through space by throwing mass away in one direction to accelerate in the other direction. This is all in accordance with Newton's third law and the conservation of momentum. Now, they're not usually called rockets, but I am classifying ion drives, plasma drives, even exotic speculations like an antimatter neutrino drive as basically rockets because they all work this same way. Now, if conservation of momentum holds, the rocket is in fact the only possible completely self-contained space propulsion system, and somewhat annoyingly, all rockets suffer from the rocket paradox. Here's an example. We've got exhaust velocity, the speed at which you're ejecting matter, plotted across the bottom here, maxing out at the speed of light because you can't throw anything away any faster. Mass consumption goes down, energy consumption goes up. The more efficient your rocket is in terms of its use of mass, the less efficient it is in terms of the use of energy. In addition, there is the rocket equation. The velocity at which you throw away your reaction mass is pretty much a constraint on how much you can maneuver, on what total change of velocity you can accomplish. Specifically, the total mass of fuel you need, or rather the ratio of your fueled mass to the payload mass you're trying to move, grows exponentially with the ratio of the delta V, the velocity change you want to accomplish, to the speed at which you're ejecting the fuel. The blue curve here is a plot of the rocket equation in dimensionless units, just the ratio of your desired velocity change to your exhaust speed. These other straight lines are based on the chemical rockets we're building these days. The green line is the minimum requirements for velocity change for a planetary mission such as NASA is conducting right now. And the red horizontal line is our maximum engineering capability in terms of how much fuel we can cram onto the thing in terms relative to the mass of the structure required to hold it. The fact that this intersection is below this intersection is what makes planetary missions possible, and the fact that they're so close to each other is what makes them so slow and expensive. So if Conservation of energy and momentum forces the rocket paradox onto any self-contained drive. What about systems that aren't self-contained? We've seen allusions to some of these in previous talks. Light sails get thrust by reflecting radiation from an outside source. The Bussard ramjet, we saw it discussed as a fusion ramjet. I like to credit the guy who seems to have come up with the original idea. You scoop up the ambient medium as fuel. Current-carrying tethers get thrust from exploiting ambient magnetic fields. Magnetic sails get thrust from deflecting ambient plasma. The ramjet may be impossible. Collecting interstellar hydrogen is a hard problem in itself, and getting it to undergo fusion on the fly is even harder. All of the other systems are dependent on special environments or support from home. The core problem that makes all of these drives unsatisfactory, unfortunately, happens to be two basic laws of physics: conservation of energy and conservation of momentum. Now, in relativity, these are the same law. Energy and momentum form a relativistic four-vector, and all of its components are conserved. Unfortunately, you can't escape the problem just by rejecting relativity. There's something called Nether's theorem in mathematical physics, a very long-standing result. It's a mathematical proof that any continuous symmetry in a physical law leads to the existence of a conserved quantity. The result of having physical laws that don't change over time is that total energy has to be conserved. Similarly, momentum conservation follows from the fact that physical laws don't change when you move from one place to another. I step from here to here. The laws of physics are the same in both places. Therefore, momentum is conserved, according to Nether's theorem. But there is a loophole. The tensor calculus used in general relativity satisfies the defining symmetries of general relativity automatically as a matter of notation. The Nether construction becomes trivial. It doesn't allow you to compute a conserved quantity. In fact, energy and momentum conservation in general relativity have only been proven for simple special cases. There is no general proof. So the conservation laws may not hold for the full theory. In fact, when you're dealing with an arbitrarily curved space-time, such as is allowed for the theory, it becomes a little bit difficult to figure out what something like an energy density even is, let alone whether it's conserved. Digressing for a moment, for most of this talk, I'm assuming that both special and general relativity are true. Now, there's a lot of evidence for this, and any alternative theory, if it is to be taken seriously, has to match a tremendous body of observational evidence that confirms both special and general relativity. However, since there are some anti-relativists around, especially in the SSE, it seems important to consider alternatives, at least briefly. Now, general relativity is mathematically unique. It's the only theory that satisfies the appropriate symmetries, except for little bells and whistles like whether or not there's a cosmological constant. If GR is wrong, there's no way, I should qualify that, there's no way that I know of, to avoid the Nether construction, and we're stuck with conservation laws that are technologically inconvenient. However, a non-relativistic theory, by definition, admits the possibility of non-local interactions that propagate faster than light, which can create the local appearance of momentum non-conservation by having reaction forces apply to remote objects. In the most extreme case, a non-relativistic theory might allow instantaneous reaction with the entire background universe. The local acceleration of the drive might be obvious, but the reaction of all other matter everywhere would be impossible to measure. In fact, if Mach's principle is valid, it doesn't really have any meaning. Mach's principle, which has been mentioned several times for people who haven't heard of it, is simply the idea that it's the behavior of the matter in the universe as a whole that defines what is an accelerating or non-accelerating frame of reference.